Hey, how's it going, guys? Today I will quickly go over my solution to the find minimum rotated sorted array. Suppose an array of lengths n sorted in ascending order is rotated between 1 and n times. For example, this is a sorted array and it's like rotated at some point. And so given the sorted array nums, return the minimum elements in the array. So basically you're given a rotated array and you have to output the minimum number. So for example, 1, our minimum is 1. For example, 2, our minimum is 0. For our example, the minimum is 11. Notice that all the integers in the nums are unique. Okay, cool. So the brute force solution will be just an ON solution, basically just return minimum of nums, right? And yeah, so you will pass, and the time complexity will be OM, and the space complexity will be O1. Can we do better than that? Because it's a medium question, right? So there is a better way, which is binary search. So in normal binary search, we get rid of half of the array at each time, right? So how can we use binary search in this rotated sorted array problem? So I have a picture here. So when array is rotated, there are two cases. Case 2 is it's rotated 0 times, or it's rotated length of the numbers, length of the array times, so it become the original array. This is case 2, right? And case 1 I draw here. So basically imagine this is the bottom and this is the right. So basically imagine this line was originally from here and you rotate it. So basically you chop it from here and move it to here. So when you rotate an array, it's either case 2 or case 1. There's no other cases. Okay, so let's say if our midpoint is here, and the trick is, so this is my code, is very simple, and the trick is always compare. So basically initialize your left array, left index at 0 and right index at not length of nums minus 1. So, and the trick is, after calculating the midpoint, always compare the midpoint to the right point and move the index accordingly. Why we compare the midpoint to the right point? Okay, let's go back to this this one. So let's say if our mid is here, so if we compare our mid number to the right number, if it's larger, then we know that basically we have to find the bottom, right? So we know that, let's say our mid is here, we can move our left to mid plus 1 because we want to find the bottom. There is no way if my mid is larger than the right, the bottom has to be on the right side of our midpoint. Let's see case 2. If our mid is here, if it's like in this case, it will never be greater the mid value will never be greater than right. So basically, it only falls here. So you can move if your mid's value is greater than the right value, then you can move your left pointer to mid plus 1. However, if your mid is smaller than right, so your mid is somewhere here, right? It's smaller than right, then you know that your bottom can never be on the right side of the mid. It will be here. So you can move your right pointer to mid. So in this example, the same. If your mid value is smaller than your right value, then right now our bottom is here, right? So it will never be on the right side of the mid. It will always be on the left side. So that's why you can move your right pointer to mid. Okay, let's go back to the code. So right now you can see that I always compare my mid to the right value. If it's greater, then I can move mid plus 1. Else, I can move my right to mid. Okay, let's see. Why here we move mid to right instead of mid minus 1? Let's see this example, 312. Right now, our mid is smaller than the right. So we are here in the else statement. If it's smaller, if I say right equals mid minus 1, then my right will become here. And I will miss my bottom, which is 1. Instead, I have to move my right to mid so that when I calculate my mid again, it will become this index and it's larger than the right at this point. So I will move my left pointer to mid plus 1. Right now my mid is here, and so right now you will never go into the loop because my condition is well left is smaller than right. I just need to return nums out. So the trick is always compare mid to the right value. So someone might say, can I compare mid to the left value? Let's see. So if the mid is greater than L, then can we move our left pointer to mid? It seems okay at this case. But here, if our mid is greater than L, right? It's greater than L. Can we move in this case, we should move our right pointer. So you can see that right here, if mid is greater, its value is greater than left, we move our left pointer, but here we move our right pointer, so it's not going to work. However, if we just compare mid to the right value, when it's greater, then we